Welcome back. So we were talking about distributed learning paradigms, and if you recall, one of the issues we mentioned was communication limitations. Okay, and in this lecture, our goal is to talk about that and also talk about approaches to mitigate that, such as approaches based on designing compression mechanisms. So again, recall that in distributed learning, we have agents that they share information with each other, or they share information with a central aggregator, central server. This information could be the raw data itself, but due to privacy reasons that we have talked about, typically that's some representation of the data. Could be the current local models, could be the gradient of the local loss functions that the agents hold locally. Okay. But nonetheless, they repeatedly share this information, let's say with the server or each other, okay? And this was a template algorithm that we discussed before. So let's say that for capital T communication rounds, server sends the global model to all agents. Each agent is going to basically compute and send, let's say, in this case, their gradients, their local gradients to the server, and server basically aggregates these gradients to update the global model. This could be based on a simple algorithm such as a stochastic gradient descent or gradient descent, or even more sophisticated algorithms. Okay. Now, what's the challenge? So one challenge is communication limitations. Okay. So what is in particular limitations of the agents or clients? Each agent in this template algorithm is required to send a vector of size d to the server. Okay, so that basically means that if we represent each coordinate with 32 bits, it requires to send 30 orders of 32 times the number of bits in each communication round. Okay, and this may not be feasible, especially in cases where the agents have low communication resources. This could itself be because of, let's say, a power limitation, because communication turns out to be basically an operation that requires a lot of power. So if you have low power devices, they may not be able to send highly precise messages each communication round. So they may need to resort to alternative approaches that we're going to talk about in this lecture. Okay. Right. So basically, our goal is to send a low precision message to a server to save on the number of bits we are communicating. Okay, so we're going to resort to compression mechanisms as a solution. Essentially, the idea is that instead of, let's say, calculating the true gradient or a stochastic gradient, we're going to send C of G, where C is some compression mechanism. Okay. So let's discuss some examples of what this compression mechanism could be. But again, the idea is that it is a mechanism that reduces the precision of our message, in this case, the gradient. Okay? So a simple example is quantization. Okay? So essentially, the idea is that instead of using 32 bits to represent each coordinate, we're going to utilize fewer bits. Okay? So in particular, let's say we reduce 32 to Q bits, where Q could be, let's say, 1, 2, 3, 4, whatever. And typically, I would say it's a power of 2. Okay. So therefore, it is easy to see that if we use quantization and communicate Q bits as opposed to 32 bits, we're going to save order of 32 divided by Q in our communication resources. Okay. So let's see an example of this. Let's imagine that I have a vector x that I want to compress, and I want to use quantization to do that. Okay. Let's say that I'm using a q equal to 1 bit quantization. That basically means that I can only communicate two options, one of two options. Let's say plus or minus, +1, -1, etc. So that basically means that if you are using a 1-bit quantization, you need to send the sign of each coordinate only. We cannot communicate anything beyond that. Therefore, in this case, that the first coordinate is positive, the second and the third coordinates are negative. what we're going to send as a result of applying quantization as our compression mechanism will be a vector where the first coordinate is +1 and the second and the third coordinates are -1, indicating that we are only communicating the sign of each coordinate. Okay, that's one approach. Another approach is based on, let's say, a sparsification. So the idea is that if I'm communicating a vector of size d, maybe instead of sending all d coordinates, I only communicate k out of these d coordinates, and also I need to send their indices. Okay. So order-wise, it is easy to see that by using this approach, we're going to save order of d over k in our communication resources. Okay. And this is very advantageous, especially in the context of deep learning optimization, where our gradient or our model are very large, orders of millions or even billions of parameters. So d is something that is order of millions or billions, and k could be something that is significantly smaller, maybe order of like 100 or 1,000. So using a sparsification, we could potentially save a lot in communication resources. So let's go back to our example, see this sparsification idea in action. Let's again imagine that I have this vector x that I want to compress, but now instead of quantization, I want to use a sparsification, such that k is equal to 1. So that basically means that I only can send one out of these three coordinates. Naturally, if we have only we can only send one coordinate, we may want to send the one that is largest. Okay, so in some sense that would reduce the compression error, which is basically the difference between what we are sending as a result of compression and what we hope to send, which in this case is x. Okay, so therefore with k equal to 1, let's say we select the largest entry. And therefore, what we would be sending is, let's say, this vector, where now, what's the largest entry? The largest entry is actually the last entry, third coordinate, because it's the largest in magnitude. So what I would be sending would be 0, 0, indicating that I'm not communicating the first or the second coordinate. And then I would be sending the last coordinate with full precision, -3.5. Now let's also talk about another idea, and that's low-rank factorization. So this idea makes sense when what we are communicating are, let's say, matrices, which is actually true in the context of deep learning optimization, right? The weight matrices, for instance, for each layer. So those are model parameters, right? That we may want to communicate in a distributed learning paradigm. Or given that there are weight parameters, the gradients or the partial derivative with respect to those will also be matrices. Okay, so if we are sending those gradients, again we are sending matrices. So one way to reduce the precision of a matrix is to reduce its rank. Okay, so therefore what we can do, let's say, is that if I have a matrix like this, I can find its factorization with, let's say, a very tall matrix U here, and sort of like a very fat matrix V transpose. I only communicate U and V. So naturally, as you can see, M has a lot more entries than the combination of U and V. So therefore, if I find this low rank factorization, I would be able to save a lot on the communication resources. For instance, let's say M is something that is, let's say, d by d, okay? And let's say U and V are actually vectors. So they are, let's say, only in RD. So if I were to find this low-rank factorization, what I would be sending would be 2 times d. So I would be sending 2 times the coordinates. Whereas if I were to use full precision communication, I needed to communicate d squared number of coordinates. So I would be saving a factor of d in my communication resources. Okay. All right. So one remark before we move on is that you can actually combine these ideas with each other. So for instance, you can add sparsify and also reduce the precision of the coordinates that you're sending by utilizing quantization. Or again, you can use low rank factorization and again apply quantization or sparsification to reduce the number of bits that you're communicating even further. Another remark is that these ideas could also be used to basically save on computation resources. Okay, so for instance, when you want to fine-tune, let's say, a very large model and use it in a low-power device, you can take the weights of the pre-trained model, find their, let's say, low-rank factorization, and then use that in the fine-tuning and also in the inference in the low-power device. So that would mean that you don't need to spend a lot of computation resources at the inference time, for instance. So therefore, not only these ideas could help us in communication savings, as we were talking about in this lecture, but could also be applied in other contexts, for instance, saving on computation resources. All right. So now we discussed a few examples on these compression mechanisms, and they are not random. They are actually examples of good compression mechanisms. So let's talk a little bit about what we mean by a good compression mechanism. Okay. So basically, what we are doing estimation. Okay. So we have some quantity, let's say G, which is the local gradient that we intend to send. Instead, we are sending a low precision version of it. So in particular, we can think of C of G as an estimator of G. Okay. So we can think of the compression as an estimator of the quantity we are compressing and communicating. So therefore, we can utilize the terminologies from estimation theory to talk about whether a compression mechanism is a good mechanism or not. And two basically sort of criteria for us are the bias and variance. Okay. So therefore, we can say a compression mechanism is good when it has low bias and low variance. Okay. So such that the total estimation error, again something we've seen before, or in this case the total compression error, could be written as, let's say, a variance term plus a bias term. So therefore, if I want the total compression error to be low, I don't necessarily require an unbiased estimator. I want the both or the combination of bias and variance to be low. Okay. All right. So here in this definition, I've also used some expectation, because many times our compression mechanisms are actually randomized mechanisms. Okay. So there is some sort of randomness involved. The examples we saw earlier are actually deterministic, but I'm going to talk about a few examples here that are actually randomized. So we're going to talk about randomized sparsification strategies and also an example of a randomized quantization strategy. Okay, so let's talk about basically, therefore, some more examples and also at the same time talk about their bias and variance. Okay, so one strategy is random sparsification. As the name suggests, what we're going to do, we're going to select K out of D coordinates, let's say uniformly at random, and only communicate those. Okay. So in terms of the bias, it turns out that, and this is not a very difficult calculation, it turns out that the expected value of the compressed quantity will be K over D times X. So this means that we're going to have some bias. Okay. Now, it also turns out that the total estimation error or total compression error will be bounded by this expression. So basically, the bound has a factor of 1 minus K over D, and also another factor that depends on the norm of the quantity that we are compressing. Okay, and I'm going to talk about this in a moment. But maybe you want to have actually an unbiased estimator. Okay, and there is a way to make this compression mechanism unbiased. All you need to do is to look at the expected value. So you see this factor of K over D, and I want to get rid of that. Basically, I want to make sure that that factor is equal to 1, such that there is no bias. So what I can do there is to define another compression mechanism that takes this random sparsification and multiply it by d over k. Okay. So essentially what is going on here is that as a result of sparsification, we are reducing the power. That's why we are incurring some bias. Now, when I multiply with d over k, I am increasing the power again. Therefore, I am getting rid of the bias. Okay. So this results in an unbiased estimator or an unbiased compression mechanism. But doing so is going to lead to an increase in the variance. Specifically, we can show with some calculation that the total estimation error, which in this case is only due to variance, is going to be proportional with d over k squared. Okay, so and d over k is, you could think of it as a very large number, for instance, 100 or 1,000. Okay, so that basically means that this, this unbiased random sparsification strategy may not be as good as the biased one. Okay. All right. So therefore, it seems that the biased version is better because it has a lower compression error. So we have a factor of 1 minus k over d, something that is between 0 and 1, compared to a factor of d over k squared, something that is definitely and significantly larger than 1. Okay, so that's one takeaway. But another takeaway is that for both strategies, as x goes to 0, the estimation error or the compression error also goes to 0. Okay, and this actually gives you a way to decide which quantity you want to communicate in your distributed learning paradigm. For instance, if you are communicating gradient, you expect the gradient to be something that is converging to 0 as you are, let's say, performing learning. Okay, because at the first order optimality condition basically says that the gradient has to be 0. So in that case, then x is our gradient. We expect the gradient to go to 0 as our learning algorithm converges. Therefore, we should expect that if we communicate the gradient, the compression error reduces as we are basically performing distributed learning. On the other hand, if we were to send models, model parameters themselves, those are not basically quantities that necessarily go to 0. So the optimal parameter is not necessarily 0. The optimal model is not necessarily the model that all the weights are actually 0. And in fact, it is not the case. So therefore, if we were to communicate the models as opposed to the gradients, we would sort of lose this nice property that the compression error goes to 0. Okay? So therefore, a result of this takeaway is that we want to communicate quantities that we expect them to get smaller and smaller as we are performing distributed learning. All right. So let's talk about another example of a sparsification, and that's top K sparsification. So it's basically a generalization of what we saw before. So again, we're going to select K out of the coordinates, except that instead of selecting these coordinates at random, we're going to select them deterministically. We're only going to look at the largest coordinates in magnitude. So it is a deterministic operator, so we will have some bias. And what we can sort of show is that the compression error is at worst the same as the expected compression error of the randomized sparsification strategy, which will be 1 minus k over d times x, norm of x squared. And again, x is the quantity we are compressing here, for instance, the gradient. So again, we have this nice property that basically as x, the quantity we are compressing, goes to 0, the compression error also goes to 0. All right. So another example of a good compression mechanism is random dropout. Okay. So the idea here is that you're going to either communicate with full precision, or you're not going to communicate at all. Okay, and you're going to make a decision by tossing a bias coin. So More specifically, so you're going to communicate with probability P. Otherwise, you're not going to communicate anything. And that basically happens with probability 1 minus P. Okay? So it is very easy to calculate the bias of this strategy by looking at the expected value of our compression mechanism. So the expected value will be P times X. We have some bias as long as P is strictly less than 1. Okay? And it turns out that basically the total compression error in this case will be 1 minus P times norm of X square. Okay. Like the random sparsification method, we can make this an unbiased strategy as well. Again, by performing dropout, we are reducing the expected power of our communicated signal. So if I multiply with 1 over P, I'll be able to, again, increase the power, therefore get rid of the bias. So I can define this new compression mechanism, which is basically 1 over P times random dropout. And this will be an unbiased compression mechanism. But like before, the consequence is that the variance is going to go up significantly. It's going to go up with a factor of 1 over P squared. Okay. So therefore, again, it seems that the biased version is better in terms of the total compression error compared to the unbiased one. Okay. So this is the second example we see that the biased operators, biased compression operators, seem to be better and have an advantage in terms of the compression error compared to unbiased operators. Okay, so that's one takeaway. Again, another takeaway is that as X goes to 0, X, basically the compression error also vanishes. So therefore, again, it is very natural to communicate gradients in distributed learning while utilizing random dropout as our compression mechanism. Okay. And basically, it should also be clear that when you do a comparison between random dropout and random sparsification, if I specify P to be K over D, the two seem to be identical or equivalent on average. Okay, and that's indeed true. Okay, so on average, these two are identical, but in practice they're not. For instance, in the following scenario, you may not necessarily be able to even implement random dropout. Okay, so let's say that in each communication round, my agent can only send a certain number of bits. Let's say only 32 times K bits. Okay, so therefore, I'll be able to utilize random sparsification because regardless of the fact that my operator is randomized, I will be sending only K coordinates, and I'll be using 32 bits to represent each coordinates. Okay. Now, on average, if I set P to be K over D, I'll be able to satisfy this requirement. Okay. However, for a specific communication round that I'm sending a message, I'll be sending 32 times D bits. Because random dropout says that you are communicating fully with certain probability, so that won't be basically possible in this case. So even though on average they are equivalent, there are therefore differences, and we may not be able to, let's say, random dropout in scenarios where there is a hard requirement on our communication budget. All right, so the examples we talked about so far were on basically a sparsification. We talked about random sparsification. We talked about top K sparsification, also random dropout. Let's talk about an example on quantization. Okay, and this is basically referred to as QSGD in the literature. So here's what we're going to do. So let's say that I have a message that I want to send in a compressed way, X. So what I'm going to do first, I'm going to sort of perform some normalization. Essentially, the idea is that I want to separate the sign, I want to separate the magnitude, and let's say I can communicate those with full precision. And what I'm left with, basically a normalized vector that's the quantity I want to quantize, okay, and reduce its precision. Okay, so therefore we are going to separate the magnitude and the sign by performing this normalization. Okay, so after this normalization, therefore, when we separate the sign and also making sure that the norm of the our signal is 1, each coordinate will be between 0 and 1. Okay, so therefore we can quantize each coordinate separately, and we can basically randomly assign them to q different levels. Okay, to obtain a vector, let's call u tilde. So therefore u tilde should be thought of as the compressed version of this normalized vector. Okay, once I find that, I'm going to send basically so what I'm going to send will be equal to the magnitude times the sign times this compressed version of my normalized vector. Okay, so there's an example here. I'm going to go talk about this in a moment, but to see exactly how we basically do this randomized quantization and find u tilde. But let's first talk about the property of this random quantization strategy. We can show that it is an unbiased compression method, and also we can derive a bound on this variance or the compression error. So it depends on D, the size of the signal we are compressing, and also S, where S is the S or Q is basically our quantization level. Okay, so if we use qubit random quantization, therefore we'll be sending O of 32 divided by q bits in the communication. But the idea is that this is going to have a very good, the error is going to have a very good dependence on the size of the vector we are compressing as well as the quantization level. So, and again, a nice property of this random quantization strategy is that the error depends on the norm of the signal square. So again, if you are compressing the gradients, the error is expected to go to 0 as we are running our learning algorithm. Okay, and finally, we can actually rescale this strategy to introduce some bias with the hope of reducing the variance. Okay, and as we've talked about before, this could be advantageous in a lot of scenarios, such as compression, that we're going to have more discussion about it in a moment. All right. So let's also talk about this example to see exactly how we can find this random quantization vector u tilde. Let's imagine that I'm looking at the coordinate of this u, the normalized signal, and that coordinate turns out to be 0.6. Okay, and let's also assume that I'm performing q equal to 5 quantization. So that basically means that I'm going to divide the interval between 0 and 1 into 5 different levels: 0, 0.25, 0.5, 0.75, and 1. Okay. Now, when I want to quantize, I have this value 0.6. I can do it in a deterministic way. I can also do it in a randomized way. So deterministic way says that, hey, this 0.6 seems to be closer to my level 0.5 than all the other levels. So therefore, I may assign it to be 0.5 and then communicate that. Okay. So that's the deterministic approach. The randomized way, on the other hand, says that let's find the levels that are the top two levels that are near this 0.6, in this case 0.5 and 0.75. Now do the assignment in a randomized way, such that the closer the level is, the higher the chance of assigning that level to our number, in this case 0.6. So as we can see here, between 0.5 and 0.75, which are the top two closest levels, 0.5 is closer, so therefore we assign a higher probability to basically 0.5 than 0.75. All right, so that's basically therefore the randomized strategy that is utilized in this QSGD random quantization strategy. So we talk about some, therefore, examples of compression mechanisms that are good in the sense that they have a low total compression error, meaning that we have some factor times, let's say, the norm of the signal square. And as the signal goes to 0, the total compression error also goes to 0. Now we're going to discuss basically the impact of compression in the convergence of our training algorithms. And we're going to do that in the next video. I'll see you there.